Just like with any other inference for means, proportions, or chi-square, there are conditions that need to be met. Here we have a helpful little acronym to help us out. It almost looks like linear, except it's just linear. These are the things you need to check. First, take a look at a scatter plot to see if you in fact have a linear relationship happening. If you don't, if it's just all random scatter, or if it's something curvy or sinusoidal, then this is not the appropriate thing to do. You shouldn't be running a regression slope because a line isn't a good model. Next, the I. Are your observations independent? If they come from an experiment, they are. If you are, going back to our example of heights and weights in Davis, if you're taking from a population without replacement, check your 10% condition. The next one is the toughest one to understand. The N, normally distributed. Are Y's normally distributed for a fixed X? Here's what that means. Take a look here at this picture. Here what we have is a regression line. Notice it's got the population numbers on it, so it's the population regression line. And what we're saying is, if you choose a particular X, so in this case, they're talking about training time. For us, this would be a height. At a given height, or training time, are your Y's, your responses, so entries per hour, or in our example, it would be weights, normally distributed for that height. So if I pick a height of 6 foot 0 inches, I'm going to get some people that have the predicted weight exactly, a few that are a little bit heavier, and then very few that are much heavier. Conversely, I'm going to have a few that are a little bit lighter, and then very few that are a lot lighter. So at a fixed height, do I get basically a normal distribution of responses, of weights? Then this is just a few different pictures trying to show that same thing. So at a particular height, are your weights bell-shaped? At a particular height, are your weights bell-shaped? For a particular explanatory value, are your responses normal? Here's another one in 3D version, and then here's that same idea. Again, looking at that normal distribution about the line. Here's the thing. That's nearly impossible to check because we don't have lots and lots and lots of measures at the exact same X. You may only have one measure at a particular X. Maybe you got two, but especially if you've got something you can measure very precisely, things probably don't line up. So here's what we do instead. Run a regression, look at your residuals in a histogram form, and see if that is unskewed with no outliers. Just like we did for the means test on T's, unskewed with no outliers. So that's the LIN. Next is the E. Is the standard deviation the same for all your X's? This is where you would look at a residual plot. So X's along the horizontal axis and residuals along the vertical axis. What you want to see is what we always want to see. Do I have roughly the same sort of random scattering above and below? There you go. If that's the case, then yes, our variation, our standard deviation is roughly the same all the way through. If, however, you see a fanning effect, maybe they start low and then get big, this is boo. Same thing in reverse. If they start big and get small, that also is boo. We want to see roughly the same heights above and below the whole time. And then lastly, the R, randomization. Always matters. Does it come from an experiment or does it come from a random sample? If you check those 5 things, those are the conditions you need to make sure are in place before you do a confidence interval or a hypothesis test.